that we have at our disposal are force of gravity is equal to negative big G M1 M2 over R squared. Okay, why is that? Why negative? Okay, look on your equation sheet. Okay, on your equation sheet, it looks like this.
Looks like
There's a little R hatty thing. Okay? All right. What's anything with a little hat on it?
average, projected, like estimated.
Estimate.
Give you a hint.
I thought it was average.
Deviation.
Approximation.
Well, we're going to call it
Vectors.
direction.
Okay, it is a unit vector in that direction, right? All it does is tell you the direction of the thing, okay? So like if we had, 26I hat, then we know if it's meters. We know that that's in the x direction, correct?
Yes.
All right. So if I had 4 meters per second r hat, what would that mean?
Or along the radius.
Yeah, in the radial direction. And what is the positive radial direction?
Out.
The answer is outward. Okay? All right, outward from the center. Okay, so the thing is here is this is negative along the radius. So that's what that means. So when you see that on your equation sheet, don't let that freak you out. This just means the direction, which is outward along the radius, but this says negative. So it's in along the radius. Because positive radius is always outward. Okay? All right, got it? So in a sense it always does mean attract, but really mathematically it means in along the radius. Okay? All right, piece of cake there. And then last time we figured out that the force of gravity equals your weight, correct? And then we derived this, which was G equals big G M over R squared. That's big M over R squared. That's gravitational field, right? We're going to think about that a little bit different. It is the acceleration due to gravity, but it's also, in reality, gravitational field. It's the force over the mass, newtons per meter. Okay?
Newtons per kilogram.
Thank you. Newtons per kilogram. Newtons per kilogram. I'm for random unit generator today. All right. So we got that going for us. So out where the space shuttle is, the acceleration due to gravity, aka the gravitational field, is not as strong as it is here, right? But it is still in existence, right?
Yes.
Because where only does the gravitational field go to 0?
When it's negative.
At infinity, right? When you're very far away. Okay? So where the astronauts are, they're not weightless because there's no gravity. There's still a gravitational field. They're weightless because everything's in free fall. Everything's falling at the same rate. So you can simulate weightlessness. All you have to do is be falling with everything else. Okay, so like if this room was falling, and everything in the room was falling, then we would experience weightlessness. Okay? So all you got to do is take this room, take it up to a really tall tower, and drop it. And we would experience weightlessness.
And
We wouldn't go and flight to the ceiling afterwards.
No.
we experience weightlessness, fear, and death.
Yes.
No. All you need to do is to do this. Drill a hole through the earth,
So then we
take the room, and drop it. And we would, what would we do?
We would burn in the core of the earth.
Like squish together again.
Between the two sides,
Gravity.
Raul has a valid point.
What's that?
The earth would squish together by the gravity, wouldn't it?
Would Earth get squished together? No. There's a hole.
No.
Yeah, the Earth was
Gravity would
We don't. No, we.
It's a hole, not split.
We have really strong people holding the two halves of the Earth apart.
we have it lined
But
up.
That's right. We built a little device like this to hold it apart. All right.
Let's go.
Mr. Brun, wouldn't we be falling towards the center of gravity, and then we'd have acceleration past it, we go past it, and then oscillate back?
That's correct. We would oscillate back and forth. Because when we reach the center of the Earth, what's the gravitational force on us?
0.
0, because the Earth's pulling us in all directions. Okay?
I think gravity would rip us apart.
No, and that's a common misconception, is that once we get to the center of the Earth, we'd be weightless and then we'd be ripped to shreds because the Earth would pull us in all directions. The answer to that is no, because right now the Earth is pulling us all in one direction, and we're not ripped to shreds, right? We don't stick our arm out and it gets pulled off, right? So our body structure is strong enough, right? Our body structure is strong enough. Besides, at the center, it would all cancel out, so we'd feel nothing. Extreme magma heat. By the way, where would this hole have to be drilled on the Earth? There's only one place.
Ecuador?
The North Pole.
Mount Kilimanjaro.
The North
No, it
Pole.
would have to be at the North Pole.
So Santa can
To
get to
the South Pole.
And they
So
get
Santa
together.
could send presents to the penguins, right?
That's the axis for
All right, yeah, because the reason why is because at the North Pole, the Earth is spinning like this, right? And so when we fall, we would be spinning like this. It's no big deal, right? But if we're at the equator, we're rotating around like this. And so think about it for a second. If this is the hole through and the Earth is spinning this way, when we begin, we have a velocity this way, but the velocity at this point is 0, right? The velocity over here is this way, right? So when we fall, we're going to be going faster than this part of the Earth, and we would scrape up against the nice burning hot magma as we fall through, right? So we cannot do that. We can only do that at the North
Oh,
Pole.
so we can only fall through the giant hole to the North Pole.
That's correct.
Okay.
Yes, we want to make this realistic. Exactly correct. I mean, because we're not making things up here. We want to study real physics.
Right. There's friction.
That's right. There's friction against burning hot magma.
No, but I thought he said in the word of physics there is no friction.
Because it would be silly to have frictionless burning hot
What about
magma.
the air drag as we fall through the center of the
That's why you have a propeller on the top.
Earth?
Yes, of course. Yeah, there's no air down there in the tunnel with the burning hot magma. The magma burns up the air, see? So it's no drag.
So there's no air now.
That's right.
There's no air for that area.
We have like a tank strapped to our back.
Of course, and it's weightless, so you don't have to worry about how heavy it is. Because it needs to be big, 'cause it's a long trip, right? But you could deliver mail to the other side of the Earth that way. That'd be cool.
No,
You drop mail in,
Or
and it would go all the way down to the other side, and then you'd be waiting there on the other side. The mailman on the other side would wait,
But it wouldn't get
and
to
it would
the
go
other side, would it?
whoop, and then you just grab it.
But it wouldn't get to the other side, would it?
Sure.
Would it oscillate?
Oh, yeah, but it would oscillate. It would go all the way out,
It would go all the way out?
and then all the way back.
So, Mr.
If
Burns,
there's no
So if they
friction
miss it-
in our realistic
So if
situation
they
here.
miss it, it's gonna have to wait like another.
so Mr. Burns,
Round.
just as high as you hold
If
it
it
above
misses,
the
you're
air,
like, oh.
Right.
on the other side.
So Mr. Bruin, how fast?
Assuming we don't have any friction.
How fast
That
would
would
we
be
be
good.
going?
Fast.
You dump a package.
Okay, we can find
You
that.
get
We
it.
can
You're
find that out.
like, no, we don't.
Okay, here everyone, here's the next thing we need to talk about. We need to get moving because there's things we need to cover, or otherwise you're going to fail your exam.
Like actual physics.
And I'm not going to be here to help you out, so. What was that?
Bless your soul.
Oh, I thought you said blast my soul. Wow. Very, very vindictive. Okay, here we go. Now, we know from Kepler and his crazy laws that objects are probably not circular orbits, right? That when he did his calculations, they were off by a slight bit when he was trying to figure out where the planets should be at what time. And it annoyed him, and because he was a stickler for details, he said, you know, if it's not off by much, but it's a consistent amount off, and so he's trying to figure out what's wrong with it. So he ends up coming up with the idea that they're elliptical orbits, and it comes out nice and perfect. Yeah, so, but the ellipses were nearly circular, okay? Most of the planets are in nearly circular orbits. Actually, right now we're approaching our closest approach to the sun. Okay, in the wintertime, we are closer to the sun than we are in the summertime.
Which is weird. No,
We would die in the summer.
So why are we colder now?
We're tilted.
Because we're tilted and the sun's rays are hitting us at an angle instead of straight on, and so we're actually getting less net sunlight because the sun hits us at an angle. Okay? Since we have less net sunlight, it's colder in the wintertime even though we're closer to the sun. So in the southern hemisphere, they're closer to the sun during the summer.
So do they
So-
get more heat?
In theory, they should be warmer than us. But in practicality, it doesn't make a lot of difference. And the reason why is, if you look at a globe, when you look at the top, what do you see mostly?
Ice.
You see mostly land. If you look at the southern hemisphere, you see mostly water. The southern hemisphere is it's mostly water. And so, since the southern hemisphere is mostly water, it has a bigger specific heat capacity, so it takes longer for it to warm up and cool down. So in practicality, there's not a lot of difference. Yeah. So the Earth goes around in a nearly circular orbit. Nearly circular. Okay, so if we assume it to be circular, then the force on the Earth is the force of gravity. Gravity. Force of gravity, but this is a centripetal force, which equals mv squared over r, right?
Yes.
But the force of gravity then is big G m1 m2 over r squared equals mv squared over r. Now one of these is the sun and one of these is the Earth. Which one's this?
The Earth.
This is the Earth, so the Earth goes away. And we're left with, one of the radii go away. And we're left with this, that the velocity of a circular orbit equals big G, big M over R square root, okay? You got to be able to derive that. We had to do that last year as well. For a circular orbit, the velocity of the orbit is big G, big M over big R square root. Okay? Now, how do you find the velocity of the orbit? How do you find the velocity of a circular orbit?
What?
How do you find velocity?
Isn't that what?
Distance over time.
Oh.
So what do you call time?
Period.
Time period. What do you call this distance?
2 pi r. 2 pi r.
Yeah, not pi r squared, 2 pi r, right?
Yes.
So this is the same thing as 2 pi r over time period equals big G, big M over r square root. Okay? But this r is the same as that r, right? So that's big R. Alrighty? Okay, we're going to do a little math here. If we square both sides, we get 4 pi squared r squared over t, big G, big M over r.
T squared.
Oh, thank you, t squared. Thank you. All right? Now I'm going to move the t to one side and everything else to the other side. Okay? And when I do that, I get t squared equals big G, big M. No. I get
4 pi squared.
4 pi squared r to the third over big G, big M. Is that right?
Yes.
Yes. All right? Okay.
That explains.
You remember Kepler?
Yeah.
His crazy time period squared equals some constant times radius cubed?
Yes.
There you go.
Oh, I don't
Okay.
remember that.
Makes a lot of sense.
That's derived from circular motion, assuming circular motion, and the Newton's law of gravitation. So there you go. You got to be able to derive that. T squared equals 4 pi squared r to the third over Gm. Now that we've done that, I want you to get out your review packet real quick. In your lovely and marvelous review packet. If you look at this one, it says, a student is given a set of orbital data of some of the moons of Saturn shown below and asked to use the data to determine the mass of Saturn. Assume that the orbits of these moons are circular. Okay?
We would have to use significant digits
Very nice. Thank you for bringing that up, because I hadn't thought about that. This is an experimental type problem, a lab-based problem. So therefore, we need to consider significant figures. So when you put data in that table, it better have 3 sig figs. Okay? All right, now it says, you write an algebraic expression for the gravitational force between Saturn and one of its moons. Okay, do that quick.
Do we have to do that R calculation?
No. But you just need to make the symbols look correct. Okay, this shouldn't be a hard problem. Force of gravity equals big G, mass of Saturn, mass of a moon, over a radius squared. Now you can have a small r. Actually, I can put big R simply because that's the way it's listed in the table. Big R. Okay? If you would like to put a negative, that's fine. Plus or minus, it doesn't matter. Technically, if you're going to really be correct, you could put that. Okay? I think they gave points either way. All right, now it says, use your expression from part A and the assumption of circular orbits to derive an equation for the orbital time period of the moon as a function of the radius. I see a lot of you are doing this. A little drool coming out of the side of your mouth. We just did that, everybody.
Yes.
Okay, we just did that. All right.
Do we actually have to go through all the derivations?
Yes. This is worth 3 points. The very first point is for showing that the force of gravity is equal to the centripetal force. So showing that the force of gravity equals mv squared over r. The second point is for doing this switcheroo, that the velocity equals this. That's your second point. So your first point is this, your second point is this, and your last point is the answer right here. Okay? Because they figured those were the 3 biggest important things in the problem. Okay? By the way, you only got 1 point for the first question because it's really straightforward. Okay? So far you're up to 4 points. Okay, now it says, part C, which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? Okay, what quantities would you graph to produce a straight line so that the slope of that line could give you what the mass of Saturn is?
Can we do it, y equals mx plus b thing, and find out what goes in m?
Exactly. That would be my suggestion. Anytime they tell you to graph a straight line, write this, y equals mx plus b. Here's your graph, here's y, here's x. Find whatever equation you're thinking about using and match it up with this and figure out what's going to go on the y-axis, what goes on the x-axis, what's going to be your y-intercept, and what your slope's going to be. Okay?
Well, the slope is its mass. So leave
Will
it
the,
in.
does the slope have to be exactly mass?
No.
Or it can be some constant times mass squared divided by mass squared, square root of mass. It could be any of those things as long as you know everything that's in that slope number, right? Except for mass. So you can find out what mass is, right? Okay, that's the key. You need to know everything about this except your one unknown, right? And all the numbers you can plug in, right? And then you can find what your slope is, and then you can equate them to find mass. So it doesn't have to be exactly slope equals mass. In fact, they rarely are. Okay? So here's the question. Why did they ask you the first 2 questions? To make sure that you're on the right track.
So that you're using part C.
Okay, now think about it for a second. Thinking about what you did in part A and in part B, how could you use that to figure out what you would graph to find out the mass?
Graph.
This single test question had the lowest grade on it. It was like students got like 1 to 4 points for that first part, for those first 2 parts, and then totally disintegrated after that. Okay? For this single question here, and then students gave up, even though they gave you points, even if you graphed something crappy. Sorry, bad. They still gave you points later. Okay? So here you go. See this right here?
Yes.
What are my variables?
Wait, what did you
R,
say?
R.
This is my variable,
R.
and this is my variable. I'm looking for this. Does that look like y equals mx plus b?
Yeah.
Sure it does.
Kind of, maybe.
Right here. You see it? You see it?
Oh,
y
yeah.
equals
And
mx plus b. Where's the y-intercept?
it's 0.
Should be at 0, right? So if I was going to graph this, it would look like this. I would have t squared on the y-axis. I would have 4 pi squared over gm. That's my slope. I'm going to have r to the third on the x-axis. And it should be plus 0. Now, it may not be plus 0. It may actually cross somewhere other than 0, 0. That would be an experimental error. And so to eliminate that problem, the slope doesn't depend on the y-intercept, right? So that's why we wouldn't pick one single point off this graph. So like, say my graph looks like that. Okay? Here's the problem that a lot of students will do is they'll pick this point, they'll go up, and they'll go over. They have this number and they have this number. They'll plug that in there, and solve for m. Now that's great if it actually passes through 0, 0, right? But what if it doesn't pass through 0, 0? How do you eliminate that problem?
Pick another one.
Yeah, what you do is you take the slope, because the slope depends only on that thing right there, right? Not on where it crosses through. Does that make sense?
Yeah.
Okay, so that's why when we make these graphs, the best data we can get from a graph like this is the slope. Because the slope, with our best fit line, is our best average of the data, and then we eliminate any systematic error by using the slope and not just one point. Does that make sense?
Yes.
So the slope is equal to this. So all we have to do is graph t squared versus r cubed. Now if you want to be crazy, you can do all kinds of things if you'd like. Some students said, I'm going to graph t versus r to the 3/2 power.
Wow.
By taking square root of both sides. Okay, don't make life hard on yourself, right? You know, some students will put square roots over here. That's fine if you want to. But there's lots of different ways to do this. You could graph r down here versus t to the 2/3 if you like. And that will also come out with the answer. But your slopes will be different. And you'll have a crazier slope to deal with, right? Okay, so I just wanted to start you off on that one because graphing and getting a linearized graph. We've done this stuff before, but I just wanted to remind you of how this stuff works, right? This was a particularly hard one for students, for that just graph part. The rest of it's really not that bad. You fill in the table, you graph the darn thing, and you find the mass of Saturn. It's not very hard, really. Mathematically, it's not that challenging. It's just figuring out what to graph, okay? Now, I think I have another one in here as well that's linearizing a graph. And I want you to go, that's on the opposite side of the one I crossed out, number 15. Go to the other side of that one. It's problem number 62. Okay? You go to problem 62. We're going back to springs for just a minute, since we're on this topic. It says a non-linear spring. What the heck's a non-linear spring? Or maybe better yet, what the heck's a linear spring?
Well,
It's a Kirby spring.
a linear spring is kx.
There you go. A linear spring would be where the force of the spring depends directly on the displacement. So it's F equals Kx. Okay? So a linear spring would be something like this. F equals negative Kx. Linear. It's a Hookean spring. That's exactly right. It follows Hooke's law. That's exactly the terminology, too. It's a Hookean spring. All right, now, in our problem, we have, what? Ax squared. Now, they discreetly drop the negative sign, but it wouldn't be a spring if that was not negative, right? They're just leaving it as a positive constant, but it doesn't matter. We know that it's going to have to pull backwards, right? So this is nonlinear. This is a square spring. You know what? Sometimes on the test they'll do this.
Nice.
And sometimes on the test they'll do this.
Wow.
Oh, to the 1/2. Okay, you'll see crazy things, or maybe to the 2/3 power or something like that. Okay?
It's just getting
So it's a nonlinear spring.
So what does it look like?
Looks like a spring. Actually, there will be some materials, like for instance, an elastic band. You know, like those workout bands, things like that, or rubber band. Same thing. Okay, on a rubber band, when you first start to pull it, there's not a lot of force, and as you go farther out, it gets harder and harder to pull. But like a regular spring is like that too. But with like an elastic band, when you pull outward, the force doesn't increase linearly. Have you ever worked out with a workout band? When you get to the end of those suckers, they're really hard to extend. So their force versus displacement, instead of looking linear, they look like this. Actually, for like an elastic band, there's only one way, right? It's a one-way elastic. So it only goes this. You can only extend it. You can't compress the darn thing. So it goes like that. Okay? So their potential energy functions will look different as well. All right?
So a linear spring, like no matter how far you pull it, it's gonna take the same force.
Yes. Now, we know in the real world, for a real spring, that if you stretch it too far, it's going to go plastic, right? And you're gonna extend it and it won't come back, right? You'll deform the darn thing, right?
Yeah.
So when we're talking about these springs in physics class, a Kx spring, a Hookean spring, we're talking about only that linear part. Even if you extend those out beyond, they'll start to be nonlinear at some point. Okay? But we'll leave that for your engineering class to discuss. All right, it says, they got data on the right. Which quantities should be graphed in order to yield a straight line?
force versus squared.
Okay, now this one is much easier, right?
Yes.
F equals ax squared. Well, that's pretty easy. Y equals mx plus b. Well, there's on the y-axis. There's on the x-axis. That should be your slope, right? So you should graph x squared here and f here. Piece of cake, right? That one's not so bad. Okay, when you make this or calculate this data in the table, they were very bad people.
One significant digit.
They got 1 sig fig, and then they got 2, and then they got 3. Okay? So, yeah, I'm thinking you're going to be okay with 2 sig figs in that, as long as you don't have 6 or 4.
I know in chemistry you get like 1.
Yeah, I think, like in this one, I think they would give you quite a bit of leeway. I think 1 would be too small because you'd be rounding off like the latter parts of the data too much.
Yeah.
So I'm thinking 2 would be just fine. Okay? All right. Now, I want you to notice a couple of things. Where was I on this one? Here we are. Yeah, apparently on the grading scheme, they were looking for 2 sig figs, even though the first set of data only had 1 sig fig. Okay, so part A, what do you graph? Part B, calculate the values, put them in the table. Part C, plot the darn thing. Notice on the plot, you're going to have to use good graphing skills, right? Make sure on your graph you do these things. I wrote what I'm putting down here, but I didn't write my units. Meters squared and newtons. Now on that really crazy graph that we had, T squared R to the third. That's seconds squared meters. Actually, I think it was meters to the third. Okay, meters cubed.
Yeah, it was weird.
All right.
A radial volume.
Yeah, it looks like a volume, right? You're plotting.
What's the volume of the orbit?
What's the volume of the orbit? I'm going to ignore that question.
Thank you.
Excellent. All right, part E of this problem. It says the spring is then placed on the floor. One end of the spring is fixed to the wall. The cart of mass 0.5 kilograms moves on the floor with negligible friction and collides head-on with the spring, compressing at a maximum distance of 0.1 meter. What kind of problem does this sound like?
Or momentous energy. Sounds like a momentous problem.
Yeah.
I think it's.
Is it momentum?
No.
Well, there's no time.
Can we use conservation of momentum on this problem? Part E.
No, because it's.
Okay, well, actually, and whether it's linear or not wouldn't matter. The thing is the spring free to move? No. So can we use conservation of momentum? No. All right, now, do you want to use forces?
No.
Well, maybe. You could maybe use forces. Force, distance, okay. Maybe forces will be in order. Could you use energy?
Yes.
Find an equation for energy. That is already non-linear.
Excellent. All right. All right, here's the question I want to get to. Is that we could use energy, but will we be able to use this?
No.
No. Can we derive something?
Once you do like work.
Now, could we derive something for that? You bet. Okay, here we go, everybody. How do we find energy for a spring? Well, remember, the energy in the spring equals the work done to compress it, right? All right, so that's integral F dot dx in our case, right?
Yes.
Okay, what's our force?
AX squared.
Our force is ax squared dx, integral. So when I integrate the darn thing, what do I get?
1/3 AX cubed.
1/3 ax cubed. So that is the potential energy for this type of spring. Okay? Now, or you could just think of it like the question they asked. Now, you know what? Well, it says part E, calculate the work done by the cart in compressing the spring. So here's my spring. Okay, this is not working for us. Here's our spring. It's compressed at distance 0.1 meter. And I want to find out the work to make that happen. Okay, you could either do one of two things. You could either figure out the change in kinetic energy, right? Or you could figure out the work that's done, right? Which is essentially what we did here, right? Here's the work to compress the spring. All right, there you go, and there you go, and you just put in,
That's really easy.
we're going from there to 0.1, right? So it's not that big a deal. Oh, thank you. The work done by the spring, not a big deal. What I want to caution you on, so finding work is not that big a deal, all right? And work equals the change in energy. What I want to caution you about is our graph is this. Our graph is force versus x squared. Can we find work from this graph? Because we can find work from this graph, right?
Oh.
If we had a graph like this, we could find work by just finding this area, right? Area equals work, right? Can we find, if this graph looks like this, can we do this? Will that area equal work?
No, because it's
No, because it's x squared, right? You got to be careful if you have some graphs that are of different things down here because you've graphed it different to make it linear, then you can't just find this area directly from this graph. It won't work because the area of this graph will be Newton meters squared, not Newton meters, right?
Right.
So check the units. If the units don't come out right, it's no good. All right. So there you go. I wanted to kind of go over those. So any guesses if there'll be a graph on our exam?
Yes.
Maybe.
It's going to be
Perhaps.
power of 1/3,
Haha.
4/9. It's going to be gross.
12 20 seconds. Square rooted. Okay. So let's go back to orbits. And this thing ties back into what we're going to talk about anyway. Okay? Because spring force is a conservative force, right? It's dependent on location. And gravitational force is dependent on location. So let's just figure out gravitational potential energy real quick. Alrighty then. So remember that the conservative force, oops, I keep writing G here. The conservative force is equal to negative du ds, the negative first derivative of displacement is the conservative force, right? But we want to look at that a different way. We want to rewrite that the change in potential energy is equal to negative integral F dot ds. What's F dot ds? That's work, right? The work done by the conservative force. So conservative force, so this is the work done by the conservative force. The negative of the work done by the conservative force equals the change in potential energy. These statements are all the same. They're just rewritten either in integral form or differential form. Yeah.
Sorry, what's DS again?
Or C.
The S is a distance displacement in any random direction. So, like for a spring, we'll use X. For gravity, we're going to use R. Does that make sense? Whichever the appropriate direction is. Okay, so we're going to redo this for gravitation. So I want to find out what gravitational potential energy is. Okay, so I write in here that for gravity. So this becomes dr for us for gravity. Okay, so I write negative integral negative big G m1 m2 over r squared dr, or dot dr technically, equals change in gravitational potential energy. Okay? Alright, negatives go away. Nice. Let's pull all the constants out front. Big G, m1, m2, integral dr over r squared equals change in gravitational potential energy. What's this integral? Negative 1 over r. So this becomes the change in gravitational potential energy. Oops. Negative G m1 m2 over r. Now, technically, we got to take a couple things into account. Now, there are a couple of ways that we can discuss this or not, but we neglected our constant, right? Or we have to do this as a definite integral, one of the two. All right? My engineering background tells me to do it as a definite integral. Your math background may tell you to do it as a constant plus c and then figure out what the constant is. It doesn't matter. But here's the deal. We're going to integrate from where there's no gravitational potential energy to wherever there's gravitational potential energy. Okay, where is there no gravitational potential energy? Where is the spot where there is no interaction anymore?
In the entire universe?
Yes.
Nowhere.
There is somewhere.
The center of the mass that
Dark matter.
causing
Dark matter.
The center of the universe?
Very, very, very far away. Where the interaction ceases to exist, right? That's the only place. So we're going to integrate from very far away
Very not far away.
and integrate into this spot right here. Okay? So we're going to go from infinity into R. And when we do that, we get infinity into R. So this just becomes the same. When I put infinity in there, it becomes
0.
0. Hey. Yeah. Voila. And what that does is this. That's final minus initial. So the gravitational potential energy at R minus the gravitational potential energy at infinity. And here's the cool thing about what that does. What's this value?
I thought we started with
0, right? So what we end up with, no, it's final minus initial when you do delta. So what that does is gravitational potential energy at a spot, because we picked our 0 spot to be at infinity, if we integrate from there, then gravitational potential energy at any spot in the universe is equal to negative G m1 m2 over R. Voila. Negative. All right, we probably did. All right, now negative, negative, negative. That's bad for our sense of math because we don't like the negatives. But let me show you that it all works out okay. If I take a baseball and I drop a baseball, I let go of it, it falls, right? What happens to its gravitational potential energy? It decreases. Now we're going to make this a little bit broader statement. We say that it decreases, right? So, because we say h equals 0, so it goes from whatever to 0 as it falls, right? But what if there's a hole here?
It becomes more negative.
It goes to negative. So here's the deal. Gravitational potential energy. Remember we said that all energy, if it's potential, given the opportunity, wants to go away and turn into something else, right? Turn into kinetic or something else. Okay, so given the opportunity, potential energy decreases naturally. We always say decrease. What we really should say is it goes towards more negative. It goes towards more negative. So like here is our gravitational potential energy graph. It looks like this. It's 1 over R, but it's on the negative side. So let's say here's our planet, our sun. Here's our planet out here, and let's say we just drop that planet. And so the planet falls this way, right? From this radius to this radius. Okay, what happens to its potential energy? It begins here, and it goes towards here. Do you see that it goes towards more negative? Does that make sense? Because our 0 point is set so that all the potential energy for gravitational potential energy in general is always negative. All right? So it's the same thing we have in regular MGH gravitational potential energy. It just looks weird because our 0 point makes all of our potential energies negative. Okay? All right, now, this brings up an interesting idea. Let's say that you're standing on the planet, and you don't like this planet, and you want to leave. So here you are on this planet. And let's say it's our planet. There's the mass of our planet and the radius of our planet. Okay? You're standing on this planet. Right now, how much energy do you have?
It depends. Well, like the Earth, the planet's moving, right?
You're not moving. Let's just say the planet's sitting there. Make it easy. Okay?
Yeah.
Do you have gravitational potential energy?
Sure.
Yeah, you do. Because now, if we think about it in terms of overall gravitational potential energy, that's negative G m1 m2 over R, oh, almost said squared, over R. So you have a potential energy when you're here. Now let's say you want to leave.
You need S.
Okay? if you want to leave and never return, you want to jump so high that you don't come back. How much energy do you need to give yourself? Now, I want you to notice your total energy to start is a negative number. It's this number right here. Your total energy to start is that plus that. And so your total energy to start is negative G M1 M2 over R. And if you want to not come back, where do you want to be? Very far away. When you're very far away, what's your gravitational potential energy? And if you jump with just enough energy to get you there, and nothing extra, your kinetic is this. That's the minimum energy required for you to get gone, right? So if you want to get gone, you got to give yourself zero energy.
You have to get to zero energy.
You have to get to zero energy, because where are you starting? You're starting down here, and you want to get to zero. So you got to give yourself this much energy.
Never been so happy to shoot for zero.
That's right.
So how
You're
will
shooting
you-
for zero. Aim your sights high.
How do you have zero kinetic energy? Well, like,
You have just enough energy. So, like for instance, if I jump normally, and if I jump like that, my gravitational potential energy goes from from more negative to less negative, right?
but it turns back.
But then it goes back to that, right? Okay, so here's the deal. When you jump, you give yourself kinetic, but you have negative that, right? For a total of negative total energy, because you're only able to get here, where you still have kinetic equals zero, and all of your kinetic has turned into potential, and you have the same energy you had before. Does that make sense?
Okay, I understand.
So like for instance, let's say, I'm just making up some numbers. Let's say you have negative 1,000 joules of gravitational, and you give yourself 100 joules of kinetic. Your total energy is still negative 900 joules, and so you're only able to get right here, where you're up to negative 900 joules. You still have negative 900 joules total, but your kinetic's gone to zero. You're not gone. To be gone, you have to get up to a potential energy of zero. That's gone. Does that make sense?
Yes.
All right, so that's the deal. If you want to leave, then you have to add on to this a kinetic energy that's equal to that, right? This kinetic energy has got to be equal to positive G M1 M2 over R for you to get away,
Well,
not to return.
so very far away, wouldn't your kinetic be
Zero. Now, if you give yourself more energy than that, then when you get away, you have energy left over and you keep moving.
Past infinity.
But I
To
thought
infinity and
energy
beyond.
turned into different forms, so the UG would turn into kinetic.
The kinetic is turning into potential as you go away, as you slow down. Okay? It's weird because we have negatives here, right? It's messing us up. So here's the deal. Look at our graph. Here's our graph of energy. Our potential looks like this. We're starting at the Earth's radius right here. We start here. If we want to be gone, we have to give ourselves this much kinetic to get us to here, so we never return. If we give ourselves this much kinetic from here to here, then this part of the kinetic from here to here will be eaten up by fighting away the potential energy, right? Eaten up by the potential energy, giving us this much kinetic energy left over. Right? Ooh, negative numbers messes our brains. It does. Yeah, the negatives are what's messing you up, because you're used to being here as zero, right? All right. But we're starting at a negative spot. In order to leave, we have to have more than negative. Okay, here's the general rule of thumb, and we did this in modern physics last year. Remember last year when we had energy levels? Okay? And we said down here we might have negative 13 EVs, and then we have negative 7 EVs and negative 4 EVs, and then we finally got up to 0, right? And remember we said the electrons down here were bound. They were trapped. They were in an energy well. And in order for them to leave, you had to give them at least 13 joules of energy to get gone, right?
Yeah.
And if you gave them 15, 13 would be eaten up, breaking them free, and 2 would be left over for them to fly away free.
Okay.
Same thing here. You're in an energy well.
Is that really what?
Okay. That makes sense.
You're in a gravitational energy well. And for you to leave, you have to give yourself that much energy to get gone. If you give yourself more than that amount of energy, then you get gone and fly away free.
So when you get gone and fly away, how are you moving? Are you moving?
Yeah, well, yeah, that's kinetic energy.
But
Got it? All right, so let's calculate quickly. What's the amount of energy you need to leave the Earth? So here you go. If you're on the Earth right here, I want to get energy equal to 0, so I'm gone. By the way, I never finished my statement. So if you have negative total energy, that means you're bound and trapped. All the planets have negative total energy. If you add up their potential and kinetic, it's going to be negative number because they're trapped by the sun. Okay? If an object has 0 energy, it has enough energy to escape. Well, we're just talking about in reference to the sun. The sun has negative potential energy in reference to our galaxy.
Oh, my God, so you keep going and
Yes.
for infinity.
Right, and see that was the big question is how much energy does the universe have? Is it negative, going to recollapse? Is it 0, so it goes out and stops? Or is it positive, ever expanding? And the answer is,
we don't know.
it's positive. It appears like we're accelerating out. And where is this extra energy coming from to make us keep going outward? They don't know. And that's called dark energy. That's the energy making us accelerate for some unknown reason. Woo!
Maybe we're being sucked into another galaxy.
If we were
Another
expanding
universe.
into other universes, what would happen if they hit?
Is the force attracting the universe?
There would be a turf war. I don't know.
I think we're being sucked by another universe and trying to keep accelerating.
All right.
The big vacuum inside.
So when right, yeah, what's happened is the cleaning lady has come around and decided to suck up our universe. It's making a mess, and that's why we're expanding into the vacuum cleaner bag.
There you go.
All right. Now, everybody, it helps when you think of these kind of energies here to think of like the electron in the energy shells or ionization energy and things like that, right? It's the same idea. Negative energy means trapped. Positive energy means free. By the way, circular orbits have the lowest amount of energy. Elliptical orbits have more energy but still negative. Parabolic orbits have 0 energy. So if you have a parabolic orbit, you go like this.
That's so fake.
Right here.
It's a sleep down.
In my mind, everything.
Parabolic orbit goes like that one time by and never returns.
It's also the Mr. Kato thing.
All right, if you have a hyperbolic orbit, you have positive energy. So you go and you do a flyby, never to return. Some comets are hyperbolic. They come by once, never to return. Some comets are elliptical, and they return, like Halley's Comet. Now, circular orbits and parabolic orbits are exceedingly rare, as in non-existent really, because they have to have just the right, either the minimum possible energy or exactly 0 energy. And we just don't see those really in nature. Nature is way too random for that. I guess there are possibilities of them out there, but most things are like almost circular but not quite, or almost parabolic, but either elliptical or hyperbolic. Okay? All right, so let's figure out the escape velocity of the Earth. Here we go. Energy, if we want to escape, energy for escape. Anyone? Anyone?
Yes,
Yes. Nemo.
Nemo, awesome. That means kinetic plus potential must be 0 to escape. That's the minimum energy. Okay, that's 1/2 mv squared equals minus g m1 m2 over r equals 0. Total energy must equal 0 to escape. Okay, one of these masses goes away. Which one?
the person.
The person, not the Earth, right? So the velocity to escape, escape.
Escape.
Thank you. I feel like I started in the middle. The velocity for escape then is 2gm1 over r square root. And if you plug in the mass of the Earth, by the way, this is the radius that you're starting with. This is the radius of the Earth you're starting at. That's the radius of the Earth and the mass of the Earth. We figure that out quickly. What is the escape velocity from the Earth?
How does, oh my goodness, 11.2 kilometers per second sound?
11.2 kilometers per second sounds very fast and correct.
And crazy.
Now, 11.2 kilometers per second, that is really fast. That's why you can't throw a baseball off the Earth. Because you can't throw a baseball that fast.
The movies have nice ones.
Now, if you were on one of the moons of Mars, you could throw a baseball off that moon. Because the escape velocity is so small.
There's a little Mars that plays baseball.
What's that?
Yeah.
Can we jump off one of the moons?
Whoa, I don't know, maybe.
That'd be so scary.
I'd have to figure it out. Yeah. Don't jump too high, Junior.
Jimmy, I told you not to jump.
No bouncing sports. I told you, you won't come back. No pogo.
Trampoline.
Yeah. You don't like somebody, give them a pogo stick for Christmas. See ya. Now, think about it for a second, everybody. Why does our moon have no atmosphere, and we have an oxygen-nitrogen atmosphere, and Saturn and Jupiter have mostly hydrogen atmospheres?
Escape velocity.
Has to do with escape velocity and the temperature. At this distance from the sun, we get a certain amount of solar energy, which gives our atmosphere temperature. Temperature is related to velocity of the molecules, right? Hydrogen molecules and oxygen molecules at the same temperature don't move the same speed on average. Which ones move faster? Hydrogen do. Okay. In the upper atmosphere of the Earth, hydrogen and I believe helium as well are not bound to our Earth. They get hit by the sun's rays, they warm up enough, at the upper atmosphere levels, they escape. So some of them fly away. Now on Jupiter, it's colder, and it has a greater gravitational field, so they're trapped. They can't escape, so it collects hydrogen. Our planet does not collect hydrogen. And our moon, carbon dioxide and all those things, it has the heavier the gas molecule, the more likely it's going to get stuck, right? Because it's going to move slower. All right? So our moon has a very, very, very thin atmosphere. The reason why Mars has a mostly carbon dioxide atmosphere is because it's a smaller planet and cannot hold a thicker atmosphere like we do. So, there you go. Escape velocity and stuff. All right, now we need to talk about orbits.
There's way too much shit. Like, look at this. It's a graveyard. Hold on. Something about staying up. There you go.
Okay, orbits. If here's the Earth and you have something going in a circular orbit, Okay, supposedly circular.
We'll believe it.
All right, we'll believe it. Excellent. Okay. Now this thing's in orbit. First of all, you can figure out the velocity of this orbit, right? What's the velocity of this orbit?
Square root of GM over R.
Of gm over r, because you can calculate that, right? You can figure out the time period as well if you'd like. All right, now, in this orbit right here, if we wanted to go to a different orbit, remember, this is the lowest energy orbit. We can figure out the energy of this orbit too, couldn't we? The energy of this orbit would be kinetic plus potential. And that would be 1/2 mv squared, where this is v plus, or I guess minus, big G m1 m2 over r squared, right? Where r is this distance. Got it?
So,
Yes.
is the M from the mass of the thing that's...
This is the mass of the planet.
Oh.
And this is the mass of...
Mr. Burns. Energy R. What? Oh. No,
over
that's
R
R squared. It shouldn't be R
Ah!
squared.
Thank you. Right. Now for a circular orbit, circle, nice circle here. Then when I plug this in, I get 1/2 m, no, I get 1/2 big G m over r minus G m over r. Do you notice that when I plug this in, I get
Negative 1/2. I mean,
square this.
Oh my gosh, equal to 1/2.
oh wait.
It's equal to half of this, right?
Oh,
Yeah.
okay.
If it's a circular orbit.
I was like, what is he doing?
Negative.
Got it?
Oh, it's -1.
You do get
This is mass 1 and this is mass 2. Let's do that. 1, 2, 1, 2. This is 2 in the center, right? This is 1 here, right?
Yes.
So you end up for a circular orbit equaling negative 1/2 big G m1 m2 over r.
That's cool.
Okay? That's as small as it will get. Now, let's say you want to go into an elliptical orbit. This velocity is no longer valid. Okay? So now we're in an elliptical orbit. A couple things about elliptical orbits you need to know. Okay? We got this point and this point.
And we need to know the equation for
Apogee and perigee.
Which one's which? You should
Ooh,
remember
that
from
reminds me
NASA.
of NASA.
Because I always forget this.
I always forget this too, and I'm an aerospace engineer, and this is very bad of me. I think apogee's here and perigee's here. if I remember
Yeah.
right.
Aha, I got it
Apogee
right.
is the farthest out point, and perigee is the closest point. Okay? Now, I want you to notice at these 2 points that we've got things going on. We have gravity affecting their orbits, right?
Hopefully.
Gravity affects the orbit. Do we have conservation of energy going from apogee to perigee?
I'm gonna say sure.
What forces are acting?
Gravity.
Is it a conservative force?
Yes.
Yeah.
Okay, so energy here equals energy here. Now, do we have conservation of momentum?
No. Why not?
Not for that planet, right? Because there is an outside force on that planet affecting its motion, right? But do we have conservation of angular momentum for the planet?
Why not? I
Sure.
don't.
Do we have an outside force on the planet? Yes. Do we have an outside torque on the planet?
Assuming
Which way does the force act?
Gravity exists.
No, which way does the force act on the planet? The key answer is along the radius.
along the
Along the
radius.
You're writing along the radius, yes, master. All right, so here's our radius,
I'm pretty sure you get to say anything.
and the force of gravity is along the radius. How much torque does that force produce? R cross F,
0.
It's not.
R F sine 180.
0.
0. Negative, that's cosine. Negative.
Minus any zero.
All right, so we have conservation of angular momentum. Now I want you to look at these two equations and tell me which one's easier. K plus UG equals K plus UG, which is 1/2 mv squared minus, because we have a minus here, minus big G m1 m2 over r equals 1/2 mv squared minus G m1 m2 over r. This is all for perigee, and this is all for apogee. Okay, that is a true statement.
It looks difficult.
Okay, now let's look at the other statement. Let's look at this one. How do we figure out the angular momentum of this moving blob of mass?
I'm going to call it VR.
R cross mv. Right? At apogee equals R cross mv at perigee.
Yeah.
And at apogee and perigee, these are nice points because mv is this way, and mv is this way, and radius is here, so we got a 90-degree angle. So that's RMV sine 90, which is 1. So you just get RMV at apogee equals RMV at perigee. Now, which one would you rather solve?
The second
First
one.
No!
The answers
You
are
can't.
the
Actually, you
same.
get the exact same answer. You'll get the exact same answer for radius and velocity here as you get here. They're the same.
The mass is the same, too. So
It all works out.
Well, I mean, the second one. The mass is the same.
Now, the mass here, this is the mass of the object. I'm going to label this number 1 and number 2 again. This is mass of object 1. Over here, this is mass of object 1, and that's 1 and 2. Okay? So you don't need to know anything at all about this planet or the thing being orbited for this way to solve it. Angular momentum is conserved. Energy is conserved. If you can solve it this way, solve it this way.
Well,
It's
but
just
you could just say RV equals RV.
there you go. M's go away as well. So you get RV times RV. So tell me, everyone, where does the planet travel? So where does this object travel faster?
Closest to the planet.
Right here it travels faster than here. And it's a ratio of the radii. Okay? And that's Kepler's third law, by the way. That's sweeping out equal areas in equal time. It's actually a statement of conservation of angular momentum. And that's where that comes from. All right? Now, if you want to do orbit transfers, this is the way that NASA does this. What they'll do is they'll send something up into orbit. They'll start over here, put it into elliptical orbit. When they get here, it doesn't have enough energy to go into a circular orbit. Okay? So what they'll do is it would normally fall back down like this, right, into this orbit. So here, let me redraw it so it's not confusing.
Rocket boost.
So here's your Earth, and here is a circular orbit here, and here's a circular orbit out here. I want to go to that orbit. So what they'll do is they'll send it up, and it'll go out to like this orbit here, but it would normally fall back down, right, to the Earth. So once it gets up here, they have to give it a boost of energy. When they give it a boost of energy, plus energy, then they can send it into this orbit. And then when they want to get it to this orbit, say they'll start over here, they give it another boost of energy,
NASA.
and then they'll send it into an elliptical orbit that takes it out here. And then when you get up here, what do they got to do? Another boost of energy to get into this orbit.
These orbitals are fake.
That just really hurt him, you know?
All right? Now, this orbit way out here is a very special orbit for the planet Earth. It's called geosynchronous orbit.
Or fake.
Geo.
Remains of the same spot.
Wouldn't it be an H? Synchronous?
Yeah, hang on. I got it spelled here somewhere. It's all right. CH. That's where I messed up. Synchronous. geosynchronous orbit, that is an orbit where the satellite is over a certain spot on the planet all the time. Okay? Now, there's only one place on the Earth where that can happen, and that's above the equator, because the Earth spins like this. So you can't put an object in orbit like this above an Earth that spins like this and have it stay above the same spot, right?
That's another orbit.
You watch you.
Watch you.
Like you can't put one to spy on Santa all the time. Because if you put one up there to stay above that spot on the Earth, that spot on the Earth doesn't move. So it would just fall straight on Santa. You'd kill Santa.
Yes.
All right, so
Unless you make it rotate around
the orbit
sun.
goes like this. I mean, the Earth spins like this. And so you put an object in orbit above the equator. So the geosynchronous orbit is above the equator. Okay?
But isn't like the equator like tilting a little bit?
If I,
That's so they're all going like, since the Earth spins like this, then they're all going like this.
if I launched a satellite into orbit from the moon, I could have it go the opposite direction of rotation, right?
That's correct. You can have it, you can launch from the Earth and do that. It just takes more energy.
Oh, I was going to say, that's crazy.
Yeah, it takes more energy because you got to stop it
Yeah.
and go it the other way. Yes.
It could
I'm
go-
sorry, I'm backtracking a little bit. I was going through the notes that I've been taking, and I have V equals the square root of 2pm over R.
To that one equation.
I don't remember. Oh, that was escape velocity.
Oh, I need to write that.
Okay, geosynchronous orbit. We're going to go back to this one right here. If you want to be in geosynchronous orbit, then you want your time period to be 24 hours. You want the orbit to be 24 hours. And so you can go back and figure out what the radius needs to be. It needs to be a really big radius.
That would be whipping around.
Yes, it's cranking. Actually, the astronauts go faster than that. The orbit at astronaut radius, where the space shuttle is and all that, it takes them about 90 minutes, if I remember correctly, to make one orbit. Okay, 90 minutes whipping around the Earth. Every 90 minutes they make an orbit.
Get whiplash.
So that's way too fast. So we got to send it way out there. Geosynchronous orbit with a time period of 24 hours is like 26,000 miles out. That's a long way. Okay, 26,000 miles. The radius of the Earth is 6,000 miles. No, miles.
I know.
No, 26,000 miles. That's right. That's 4.22 e to the 7th meters. I had it right, miles. So it's like way out there. So like if the Earth is here, a geosynchronous orbit is way out here. It's a long way out. Okay?
You said E7 meters?
Yeah, 4.22 e to the 7th meters.
So you, the radius of the Earth,
Radius of the Earth is
and past
e to the
that.
6th. Yeah. It's a long way out. Long way. All right, what else? Elliptical orbits. Oh, my goodness.
No, that's
We
10
got to talk
times.
about gravitational field quick.
In like 5 minutes.
All right, gravitational field. Here we go. Last thing. Hey, by the way, since we have covered this kind of fast that we can get our test in by Monday, because I'm not going to be here on Monday, you really need to do the review packet.
Yes.
Or you're going to crash and burn on the test. Because you need some practice.
But he said-
Because we would normally have another day of practice, which we're not going to have. All right. Here you go. Gravitational field. Remember, electric field is force over Q. Gravitational field is force over mass. We did this already. G(m)m) over r squared divided by m, the mass of the object. So our gravitational field is just G(m) over r squared. That's gravitational field. Okay. By the way, there is a negative in here because it is pointing inward along the radius at all times.
That's the mass of the planet.
That's the mass of the planet. That's correct. It's in units of newtons per meter, no, per kilogram. But hit it again. Newton per kilogram,
Which is meters per second.
which is meters per second squared. Okay? All right, now, if you're outside the planet, the gravitational field is this. What if you're inside the planet?
Same thing.
No.
Negative.
I'm buried, so I'm dead. So.
Okay, now let's look at a shell. What if we had a shell of a planet? So all we had was a shell.
Yeah, but
A hoop of a
Is that
planet.
metaphorically a shell of a planet.
That's right, it's a shell of a planet. It's a like a basketball. Okay, I want you to notice something. You see this radius here? You see this radius here? I'm drawing this, so like this region of the shell, the basketball, is pulling this way. And this region is pulling this way, right? Now, this area of mass pulls this way, right? And this area of mass pulls this way. Right? What's the area of mass? It's pi r squared, right?
So that's how you take the area of mass.
So this thing, the area is pi r squared, right? This little area right there. And this area here is pi r squared.
Oh no.
And if it has the same density, then we can relate the density here, because the densities are the same, that the mass over here is proportional to pi r squared, the mass over here is proportional to pi r squared. Okay, now watch. Since gravitational field this way is G equals negative G m over r squared, and over here it's G equals negative G m over r squared. You have a gravitational field pulling this way and this way, right?
So you had to add up.
But the mass is related to pi r squared, right? Notice that the r squareds cancel out. So the gravitational fields are exactly the same. So if you were inside a basketball planet, you would weigh nothing.
Is that like charge?
It's the exact same thing with charge.
Yeah, okay.
It's the exact same thing with charge. As long as the charge is on the surface, as long as the mass is on the surface. So here's the deal.
That's beautiful.
What turns out happening is if you dig a hole into the earth like this, and you stand right here, only the part of the earth below your feet gives you any gravitational field, because all the stuff around you on the outside is that shell giving you nothing.
Oh, okay.
And so gravitational field for the earth looks like this. That's what it normally should look like, right? But when you get to the radius of the planet, it drops linearly to 0.
That's funny.
So it goes like that.
Delta.
So as you dig down into the earth, the gravitational field gets less and less and less.
I will, so, if you want to feel good about yourself, dig a hole.
That's right. Now, I haven't derived this because we ran out of time, but here it is. The gravitational force inside the planet is negative G m over r to the third times r. Where this is the planet, and that's the planet, that's the mass of you, and that's the radius that you're at. That's the radius of the planet, and that's the radius where you really are.
That's our hat.
No, that's real r. That's this radius right here. It's in your books. It's derived in your book.